This is lesson 1.1, Introduction to Systems of Linear Equations, and our very first lesson in this journey through linear algebra. Before we even dive into this, let me just kind of talk a bit about the linear algebra course. A lot of what we do in here is focused on matrices and vectors. And so as we look even at this introductory lesson, something that you probably learned back in a freshman algebra class in high school, you may or may not remember how to do this, but the reason that we're doing this is because, as I mentioned, matrices is a big part of this course, and we're going to use this to kind of springboard into using matrices to solve systems of linear equations. So just as a reminder, it's been a while since you've done systems. There are a few different ways to solve systems by hand or with technology. One of them is graphically, which is obviously just simply graphing the two equations and looking for the point of intersection. Another way would be algebraically, and there's two methods there, substitution and elimination. For our purposes, we're going to focus on this last one, elimination, because, as I mentioned, we're going to use matrices ultimately to solve systems, and when we use matrices, we're really using an elimination method in order to do that. And so understanding kind of how to algebraically solve through elimination is going to help get our mindsets in the right place for when we get to matrices and use the same types of operations and methods to solve doing that. So what I have is, because I would imagine that you know how to do this. Again, maybe it's been a while, so you may have forgotten. I'm just going to run through a number of examples. We're going to do mostly two variable, two equation systems. We will do one three variable, three equation system at the end. And again, just maybe as a reminder, when you're solving these, you do need to have as many equations as you have variables in order to solve it. I would also just mention that if at any point you feel like you're ready to kind of try these on your own, pause the video, do the example, and then run the video again to see if you got it right. I'm not going to really tell you to do that, but that's something that you may just want to think about as we go along. So with that, let's go ahead and get going. So example one, we've got the x plus y equals 5, x minus 1 equals, or x minus y equals 1. And just for this first one, I just want to kind of remind us how to do all the different types of methods for solving. So the first method is the graphing method. And for this one, again, we're simply going to graph both of the lines. And so if we just make our Cartesian plane here, and I'm not going to get real sophisticated on this. Again, I just want to remind you how to do this. So if I graph that first equation, it looks like it's got a y-intercept of 5 and an x-intercept of 5. And so we would just have a line that's going somewhere like this through 5 and 5. And if I graph the other one, it has an x-intercept of 1, a y-intercept of -1. So it might look something kind of like this, at -1 and 1. And if I were to actually graph this accurately and maybe even use some graph paper or something, I would notice that these two lines intersect at the point 3, 2, which represents the equation to that system. X is 3 and y is 2. The second way to solve this is algebraically, and specifically by substitution. And when we do substitution, what we're trying to do is get the equation down to a single variable. So we're going to basically take one equation, solve it for one of the variables, and then substitute it into the other equation so that we can then solve that equation in one variable. So for example, here I might take the first equation and simply write it as y equals 5 minus x. And then if I take that second equation, x minus y equals 1, I'm going to take this 5 minus x and simply substitute it into y, since y is 5 minus x. And what I have now is an equation in one variable that I can solve algebraically. And I get 2x equals 6, or x equals 3. And if x is 3, throwing that back into any of our equations, y is 2. And we see that we get the same answer that we did by graphing. The third method is to solve by elimination. And the whole point of elimination is exactly that. We're going to try to eliminate one of the variables by adding or subtracting the two equations together. Now in this case, and I've started off with a very simple one intentionally, you'll notice that the x's both have the same coefficient and the y's both have an opposite coefficient, +1, -1. So in this case, I can either add the equations, which will eliminate the y, or I can subtract the equations, which will eliminate the x. It doesn't matter which way you do this. I'm just going to go ahead and add these. If I add, x plus x is 2x, 5 plus 1 is 6. The y's cancel. Dividing by 2, x is 3. And again, if I toss it back into the equations, I get y equals 2, which confirms our other two answers. So those are the three ways that you can solve a system. Again, though, we are most interested in solving by elimination. So for the rest of the examples, that's the method that I'm going to use. And again, if you were to pause the video and try them on your own, I would ask that you also try to solve those specifically using elimination. So for our second example, we're going to take 3x minus 2y equals 19 and 4x plus 5y equals -13. So the only difference here that you can see from the first example is obviously the coefficients do not line up for either the x's or the y's. So the only thing that we need to do here is just multiply the equations by a number to get those to match up. So for example, I could multiply the top equation by 4, and I could multiply the bottom equation by 3, and that's going to give me 12x and 12x in the two equations. I can subtract the equations to eliminate x, solve for y, and continue on. So that's going to give me equations of 12x minus 8y equals 76. And then in the second equation, we'll have 12x plus 15y equals -39. So again, now that I've got the 12x and the 12x, in this case, because they're the same, I'm going to subtract the two equations. The x's cancel out. -8y minus 15y is -23y. And then 76 minus -39 is a positive 115. Dividing by -23, y is -5. And again, tossing that back into either of the equations and solving for x, x then will be a positive 3. So my solution is 3, -5. You can give your solution as an ordered pair like that, or just simply leave it as x equals 3, y equals -5. Either one is perfectly acceptable. All right, well, let's do the next one then. So again, similar idea. In this case, we're just going to multiply, for example, the top equation by 3. Multiply the bottom equation by 2. And work it out just like we did the last example. So 18x minus a 6y equals 27. In the bottom, we get 8x plus 6y equals -14. And in this case, noticing that I've got a positive and negative coefficient for y, I'm just going to add these two together. 26x equals a 13. X is 1/2. And again, if we were to plug that back in and solve, we get y equals -3. All right. Number 4. Let's just multiply the bottom by 4. So the top is going to stay the same. The bottom is going to be, let's see, 8x minus 4y equals 20. And as we go through this, you might see already what's going to happen here. When I subtract the two equations, I get 0 on the left side. I get -7 on the right side. And of course, there's nothing I can do with that, and it's not a true statement, which tells me that there's actually no solution to this system. There's no x and y value that will make both of those equations true simultaneously. All right, number 5, notice that it's almost the identical system as in number 4. And so I guess just kind of let the cat out of the bag a little bit here. When we multiply by 4, top again stays the same. The bottom, 8x minus 4y equals 20. And of course, you'll notice the equations are the same. If we were to just subtract, we get 0 equals 0. And in this case then, because it's a true statement, the equations are the same, that means that there are infinitely many solutions. In other words, those lines just overlap each other. They're the same line in essence, which means that any point on the line is going to work for the system. All right, so wrapping this lesson up, we're going to do a three equation system now. So we've got three different variables, x, y, and z. The process is exactly the same as we did before. We're going to try to eliminate variables. In this case, though, what we're going to have to do, if you've forgotten how to do this, is we're going to use two equations at a time, in each case trying to eliminate the same variable. So for example, I might choose, let me number these equations. It doesn't matter which equations you choose or which variable you choose. I think in this case, I'm going to try to eliminate x, just because it happens to be the first one. So for example, I might use equations 1 and 2 to eliminate x, which would give me an equation with y and z. And then I could use 2 and 3 or 1 and 3 to do the same thing, eliminate x to give me another equation with y and z. Now I have two equations, two variables, and I can keep solving just like we have in the previous examples. So for example, let's just take 1 and 3, for example, because those seem to be the simplest. So if I leave 1 the same, and I'll actually kind of try to dictate out how I'm doing this using some symbols and such. But first one's going to be the same. For the number 3, I'm going to take that equation and multiply it by 2. So 2 times number 3 is going to give me 2x plus 2y minus 2z equals 6. And in this case, we're going to subtract these equations. So the x's, as we're trying to do, cancel out. And I get y plus z equals 1. So nothing I can do that with that right now. But like I said, now we're going to take two different equations. For example, I might take 2 and 3. If I leave 2 the way it is, which is 3x plus or minus 2y, plus 5z equals 4. And then I'm going to take number 3 and multiply that by 3, which is going to be 3x plus 3y minus 3z equals 9. And again, subtracting, the x's cancel out. We get negative 5y plus 8z equals negative 5. So in and of themselves, these equations don't do me any good. But now when I combine the two ideas, I can now solve for y and z, much again like we did earlier. So I'm going to take this first equation, simply multiply it by 5. So 5y plus 5z equals 5. Just rewrite the second equation, negative 5y plus 8z equals negative 5. And in this case, we go ahead and add them. We get 13z equals 0, or simply z is 0. And now I just start backtracking to find the other values. So if I take the z equals 0, plug it into either one of the two equations. I'll just plug it into this equation right here. That's going to give me y equals 1. And now plugging those back into any of the three original equations. For example, if I take that last one, if y is 1 and z is 0, that means that x would have to be 2. So that is my solution to that system. Well, that's it for this lesson. Obviously, you've got some sample problems or practice problems to do in the textbook, so go ahead and work on those, and I'll see you in the next lesson.